Why do black holes have negative specific heat? Imagine a cosmic object so strange that adding energy makes it cooler, and losing energy makes it hotter. Sounds impossible, right? But black holes do exactly that. They are some of the most mysterious objects in the universe, and their thermodynamic behavior defies normal rules. Today, we're going to explore why black holes have negative specific heat and what that means for our understanding of physics. First, let's talk about what specific heat really is. It's a property that tells us how much energy you need to add or remove to change an object's temperature. Usually, when you add energy to something, its temperature goes up. When you take energy away, it cools down. That's how most things work. But black holes are different because they follow the rules of gravity and quantum physics in a way that makes their thermodynamics unique. The temperature of a black hole, called the Hawking temperature, is inversely proportional to its mass. This means that the bigger the black hole, the cooler it is. Conversely, smaller black holes are hotter. So, if a black hole absorbs matter or energy, its mass increases. Since temperature is linked to the inverse of mass, this causes the black hole's temperature to drop. That's the opposite of what happens with a cup of hot coffee or a metal rod. Instead of heating up when energy is added, the black hole cools down. Now, what happens when a black hole loses energy? It emits Hawking radiation, a form of quantum radiation that slowly causes it to evaporate. As it loses mass, its temperature rises. So, smaller black holes get hotter as they shed energy and eventually evaporate faster. This creates a feedback loop where losing energy makes the black hole hotter, which makes it radiate more. It's a runaway process that's very different from normal objects. The reason for this strange behavior lies in the nature of gravity and how black holes are bound systems. When energy leaves a gravitational system, the system tends to contract and heat up. When energy is added, it expands and cools down. Black holes follow this principle but in a very extreme way because of their event horizons and the quantum effects at play. Their entropy, which measures disorder, is proportional to the surface area of the event horizon. When the black hole gains mass, its horizon grows, increasing entropy but decreasing temperature. When it loses mass, the horizon shrinks and the temperature rises. This negative specific heat property is more than just a curiosity. It helps scientists understand the deep links between gravity, quantum mechanics, and thermodynamics. It also plays a role in theories about black hole evaporation and what might happen to black holes over very long timescales. So, in essence, black holes have negative specific heat because their temperature decreases as they gain energy and increases as they lose energy, all due to the unique way gravity and quantum effects shape their thermodynamic properties.